Hello and welcome to another lecture on mathematics for machine learning. After last lecture where we looked at metric spaces and normed spaces, today we will look at inner product spaces. So what is an inner product? An inner product on some real vector space V is a function that takes two elements of this vector space and maps it to R. Again, needs to satisfy a bunch of things. First, it needs to be non-negative and 0 if and only we have the null vector. Second, if we take the inner product between alpha times 1 vector x plus beta times 1 vector y, this is the same as alpha times the inner product between x and z plus beta y and z. So inner products are linear if we basically change one of the elements. And third, they are symmetric, so the inner product between x and y is the same as the inner product between y and x. And this of course has to again hold for all x, y, z from our space and for all scalars alpha and beta. Now a vector space that has an inner product is called an inner product space. Every inner product also induces a norm on V. So every inner product space is also a normed space, and the norm is the square root of the inner product of point x or vector x with itself. One can verify that the axioms for norms are satisfied under this definition and that they follow directly from the axioms for the inner products. Therefore, every inner product space is also a normed space and also a metric space, because every norm also induces a metric. Two vectors x and y are said to be orthogonal if their inner product equals 0. In this case, we also write a shorthand the sign for orthogonality. Now this generalizes the notion of perpendicularity that we know from Euclidean vectors. If they also, x and y, have unit length, meaning that the norm of x and the norm of y is equal to 1, and they're orthogonal, then we call them orthonormal. So x and y are orthonormal if they are orthogonal and they both have length equal to 1. For Euclidean space, so R to the n, the standard inner product is given by the sum over the products of the elements of the vectors, or written as in matrix notations x transpose times y. Similarly, it's also often written as x dot y, which is why it is also called dot product. And the induced norm by this inner product is the L2 norm in Rn. So remember, the induced norm of a dot product is square root of the dot product of a vector with itself. And if we look at this dot product here, we basically have the sum from 1 through n, so the sum over the elements of xi times xi, meaning xi squared, and this is equal to exactly the Euclidean norm. So the Pythagorean theorem that we still know from school generalizes naturally to arbitrary inner product spaces, namely if we have two vectors x and y that are orthogonal to each other, then the squared norm of their sum equals to x, the norm of x squared plus the norm of y squared. We can prove that. So first we say that x is orthogonal to y. That's basically what we can assume, which means that the inner product between x and y is 0. That's the definition of orthogonality here. Then the squared norm of x plus y equals to the dot product of x plus y with itself. Remember, the induced norm by the dot product was the square root of the dot product of a vector with itself. So the square of that is exactly what we have here. But we have the dot product of x with itself, x with y, y with x, and y with y. Now, this is 0, this is 0. So what we're left with is this term and this term, which is equal to the induced norm squared plus of x plus the induced norm squared of y, proving our theorem. The following inequality is also known as the Cauchy-Schwarz inequality. And we often use it in machine learning to prove some bounds. It's written as follows. The absolute value of the inner product between an x vector x and y is smaller or equal to the product of the norm of x times the norm of y, and that has to hold for all xy in our vector space. Equality holds exactly if they are scalar multiples of each other. That means that they are linearly dependent. To summarize, we said that a vector space that has an inner product is called an inner product space. Every inner product induces a norm, so any inner product space is also a normed space, and thus also a metric space. For Euclidean space, so r to the power of n, we call the standard inner product the dot product. It's the sum of the products of the elements. Finally, we have shown that the well-known Pythagorean Theorem generalizes nicely to inner product spaces, and similarly the Cauchy-Schwarz inequality. So with this, I want to say thank you for today and see you next time. Bye bye.